So today I am starting lecture 14 on helicopter dynamics. Today we are going to discuss transient response. I am Dr. Ranjan Ganguly. So let us now look at a helicopter blade. So a helicopter blade could be given as a beam type structure like this. It's rotating around this axis of rotation. Now let us say we create a simple model maybe of about 10 masses for this blade. So essentially we can replace this blade by 10 masses and 10 springs. Now that would create 10 coupled differential equations for this problem. But one of the things we have learned from our normal mode study is that just 3 to 5 normal mode equations are likely to give you the same answer in terms of response because higher modes typically do not participate. And this happens because most of the actual forcing which you encounter in nature is in terms of relatively benign type of functions, and therefore what you get in terms of response is also typically expressible in terms of the first few modes. So for example, for a helicopter blade, if we were to consider it to be a continuous system where we model it as a beam, I will come back to a beam type structure later, we could consider that 3 to 4 flap bending, 2 to 3 lag bending, and 1 to 2 torsion modes would be sufficient to predict the blade response. So flap motion would be something like this here. So the blade would bend in this manner and this manner. The lag motion would be in this direction. So it would be the in plane direction of bending here. That would be lag bending, and torsion motion would be similar to a twist motion here. So that is the pitching type of motion. So these are the three main motions you encounter in a typical hinchless blade, and you could typically represent a helicopter blade which would have many degrees of freedom, maybe thousands of degrees of freedom if you develop a complicated model of the blade in terms of just the first 10 modes or so, 3 to 4 flap bending, 2 to 3 lag bending, and 1 to 2 torsion modes. So now let us look at a simple example. Let us presume that you have got a helicopter rotor blade and you have managed to express it as a 4 degree of freedom spring mass system. And therefore you have 4 masses, you have 4 springs, and corresponding to each of these 4 masses you have F1, F2, F3, and F4, which are the applied forces or the forcing which are being used on this particular structure. So now I can take this system, essentially a lumped mass system, and I can write a differential equation for this system as we have discussed before. So this is very similar to a 2DOF system. We can calculate the equation of motion for this system also. Now we will generally have W dot known at time t equal to 0, so then we can solve the equation for this system for W of t. Now, of course, we are not going to do that. We are going to express this W in terms of a normal mode expansion. So essentially, let us say there are n modes here, and we have expanded W in terms of these modes. So these phi1, phi2 all the way to phi n are the normal modes, and xi1, xi2 all the way to xi n are the modal coordinates, which are functions of time. So essentially phi1, phi2, phi-n are spatial functions and xi1, xi2, xi-n are time or temporal functions. Now you know if I substitute this into the differential equation, I can finally obtain a system such as this here. This is a set of single degree of freedom uncoupled differential equations. Each of these corresponds to a particular modal coordinate xi r. Also, we know that the initial conditions can be expressed in this form here. So if we have W0 and W dot 0, we can calculate xi r and xi dot r0. And once we obtain these, we can solve the single degree of freedom system here with respect to these initial conditions. So that's a rather trivial problem. So now let us look at a particular kind of response which is very important, and that is the transient response. So the transient response happens when the forcing is zero on a system. So that would mean that SR would be zero. Recall that SR is phi transpose into F. So F being zero, SR would be zero. So essentially this would be the governing differential equation, which is essentially the equation of motion of a single degree of freedom system. Now solving this would give us xi r is AR cos of frequency into t plus BR sine of frequency into t. This we know from our study of the single degree of freedom spring mass system. So A and B are of course the coefficients which we need to obtain, and for that we need the initial conditions for the problem. So that's the solution. Now at t is 0, let's say I know w0 and w dot 0, then I can get xi r and xi r dot 0 in this form here, and therefore I can find ar and I can find pr for this particular problem, and therefore I would know the response of the system in terms of the modal coordinates. So again, remember, modal coordinates are functions of time, whereas the mode shapes themselves are coming out of the spatial part of the system. So now we want to go back to our W because that's the actual response of the system. So WT is expressed as a series in terms of phi1, phi2 all the way to phi n. So I can write it in a matrix vector form like this. I can collect all the mode shapes here, and these are the responses. So xi1 is this value here, xi2 is this here, and so on. There are n such responses of the system, and all of them have the same structure because remember, these are all single degree of freedom systems. They all have this simple type of response with two coefficients which need to be determined. Now we'll look at a simple example to put some concrete things in the mind. Let us say there is a beam and we bend it to the third mode and then release it. So essentially we have W0 is Cn phi3. That's the only thing about the beam we know. Essentially what this equation mathematically means is that we have given this beam a starting deflection at the third mode, and we have released it very slowly, therefore the velocity is zero. So now let's look at these two coefficients. So we know that AR is this particular coefficient, and that is xi r 0. Now here we know that W0 is Cn phi3, so substitute that here, you get this equation here, and therefore you get AR is this equation. Now since the velocities are all zero, we have released it very smoothly and slowly. All the Bn terms are going to be zero because remember the xi r dot is given by this equation. So W dots being zero, all the B terms are going to be zero for this system. Okay. So we are going to only concentrate on the A terms. So we concentrate on the A term here. Now we know this term, we look at it very carefully. So when we look at it very carefully, we see that this phi r t m phi 3 term is there. Therefore this term is going to be 0 for all the cases except for r equal to 3. And therefore you are only going to get A3, and A3 is going to be Cn because phi t m phi 3 is going to be m3. That's going to cancel out. So A3 is going to be Cn. All the remaining A's are going to be 0. And we go back to our W. You put all this in this equation. Remember, all the B's are 0. Only the A3 term is present. So you are going to get Cn phi 3, which is the solution here. Cn is here, and then phi 3 is coming from here, and then the cos part of the term for the third frequency. So essentially that's the output of your system. That is the response of your system. So what does this tell us? This tells us that if the beam is excited in the third mode, the response is only in the third mode, which is what you are seeing here. The response here is just the third mode, and so you are going to get this kind of vibration for the system. So this video showed you how the transient response of the system works out. We can very easily calculate the transient response of any system in terms of modal coordinate, then go back and put it in W and get the actual coordinate. Now, one of the reasons many people prefer modal coordinates is they can physically see the behavior of the system. They like to see the fact that if they excite the third mode, then the result comes out in the third mode and so on. So some of these physical manifestations of the reality are very useful for the engineers, and therefore many engineers have a good feel about the response of any structural dynamic system in terms of the modal content, and that's something to keep in mind. So if you have not yet, please subscribe to my lecture and spread the lectures in the community at large. I will see you in my next video.